This recording will cover the PowerPoint slides from Chapter 4, which discusses multiple regression. We will talk about using Excel and SPSS. So multiple regression is very similar to the simple regression model that we discussed before, except now there are multiple independent variables. So the regression model is the equation that describes how the dependent variable y is related to a series of independent variables and the error term. In most cases, what we will do when we use this multiple regression model is use it for the purposes of prediction. So the mean value of the dependent variable y is given by the set of x values at a point on the surface described by the right-hand side of the equation. In other words, if you substitute in for specific x's into your regression equation, it will spit out its best estimate of what y should be. So we use these series of different independent x variables to make predictions about our dependent y variable. And we use the same basic process as we did before. So we have our population value of y, and we have population parameters that we actually call betas, and then what we estimate in our equation becomes y hat and b1, b2, b3. But I'll use beta and b interchangeably since, in effect, we're never actually seeing population information. We're only ever really using our sample. So let's look at our regression process. You have some theoretical relationship. You believe that a series of independent variables x relate to a dependent variable y. So you use that to develop your regression equation. Then you gather sample data to attempt to estimate those unknown parameters. You estimate them by running this multiple regression, and you arrive with the B estimates of the population parameter betas. So the regression coefficients, beta 0 is going to be your vertical intercept. Beta 1, beta 2, beta 3, all the subsequent betas are determined by minimizing the sum of squared residuals. So again, just as we saw when we looked at simple regression, so your goal is to minimize the sum of squared screw-ups. So you want this regression to be as accurate as possible, and remember you're squaring them so deviations above and below do not cancel one another out. The coefficients are interpreted as the impact of the dependent variable on a 1 unit change in one independent variable, holding all other independent variables constant. So beta will tell you the 1 unit change in y, beta will tell you the change in y associated with a 1 unit change in each individual x, ceteris paribus. Then they have the same assumptions as we did with simple regression. We expect the average error term to be 0. We expect the error terms to have a constant variance, to be normally distributed, and to be independent of one another. Now, we'll talk a little about examining the residuals. In order to do this, we will plot the residuals on the y-axis and y hat, the predicted value of y, on the x-axis. So we will be able to see, the differences between what we predict and what is our error term. And what we hope is that, we don't see any real pattern in this. We should see the average clumped around 0. We'll look at standardized residuals, so they'll be like the z-score equivalent of the residuals. So they should have a mean of 0, and they shouldn't be, they should be within 2 standard deviations of that mean of 0. So they should fall within, it should be greater than -2 and less than +2. So they should fall within -2 to +2 bounds. If the assumptions are correct, that'll show that, we're following this normal distribution and we're not really seeing much of a pattern. So how many graphs do you have to do? Well, if you want to examine them against each individual x, then you would need to do as many individual residual relationships as you have independent variables. We'll actually do that in Chapter 6 when we try to examine the residuals relative to each independent variable. So multiple regression steps in Excel, same as we saw for for our simple regression, except now obviously you're adding more independent variables in your X range. Note that the columns do need to all be next to one another. We'll do the same thing in SPSS. So again, exact same steps that we saw in our simple regression, but now I've also included the information for how to get the residual plot in there. So you'll see Z predicted as your X variable, that's your Y hat, and then Z residual as your Y variable, that is your residual that'll be shown as your on your vertical axis. So here's our first example. We're looking at medical corporation sales. They have 25 sales territories. Now what's a little unique in this is the units that we have our independent and dependent variables in are different. So sales are in thousands, advertising is in hundreds, and bonuses is also in hundreds. So we're going to run this, I'll show you this regression, and we believe that advertising and bonus together both predict sales. So you would think in general, the more money you spend on advertising, the higher your sales should go, and the more bonuses you provide to your salespeople, the more sales that you should actually see. That would be our general interpretation. So I follow the steps and run the regressions in Excel and SPSS, and I come up with my regression coefficients. Beta 0 is negative 516. Beta advertising is 2.73, and beta bonus is 1.856. And I see those both in both printouts. So my regression equation would be sales is equal to negative 516.44 plus 2.47 beta advertising plus 1.86 bonus. So I could use this for predictions if I had a given dollar amount of advertising and a given dollar amount of bonus. I could plug that into that equation and it would spit out the expected sales values for me. Now, how would I interpret those coefficients? Remember, sales are in thousands and advertising and bonus are in hundreds. So if advertising is held constant, sales will increase by $1,856 for every $100 increase in bonus. And then I can also say if bonus is held constant, for every $100 increase in advertising, sales are predicted to increase by $2,473. And that's just a function of the fact that bonus and advertising are in hundreds while sales are in thousands. A generic way of saying this, for every 1 unit increase in X, Y will increase by beta CP for ceteris paribus, meaning holding everything else constant. Then I can look at my graph of my residuals here, and again, my x-axis is my predicted value, and then my y-axis is my standardized residual. So I'm showing the same graph. The first is from Excel, the second is from SPSS. None of my observations fall outside the positive to negative 2 bounds. So I really wouldn't say I have any outliers here. I don't see any clear pattern. They just seem to be randomly scattered around. So that tells me that I'm probably doing pretty well on my 4 basic assumptions for OLS. And again, we'll learn how to confirm that, that first impression in Chapter 6. So let's go and examine the coefficients. We can make an estimate of the change of 1 unit of the y variable, of the x variable on y using that interval. Now, so what this does is gives us the confidence interval, for those of you who are interested in the math of how it's actually getting that 95% confidence interval of the impact. It's looking at that beta plus or minus t, the t statistic, times the standard error of that beta, where n is the sample size and k is the number of independent variables. In this case, K is 2 because we have two independent variables, bonus and advertising. And this 95% confidence interval is automatically going to be spit out by Excel and SPSS as well. So I can see that I am 95% confident that for every $100 increase in advertising, sales will increase by between $1,902 and $3,044 ceteris paribus. And for bonus, I can say I'm 95% confident that for every $100 increase in bonus, sales will increase by $371, roughly $372 if I round, and $3,340 ceteris paribus. So that's my interpretation there. And again, I find this information in the lower and upper 95 and in Excel, and then look at the 95% confidence interval of beta and the lower and upper bounds there in the coefficient section for SPSS. And of course, I ignore that constant, that intercept, that's my beta 0. That tells me what sales would be if I didn't have any advertising or bonus. So that number really has no logical interpretation because it's kind of hard to have negative sales. Okay, so testing the coefficients, our default hypothesis is we want to know, does this independent variable add value to our regression? In other words, is the beta coefficient equal to 0 or is it not? And this hypothesis is default tested by both SPSS and Excel, and we can find the p-values in the p-value section of your Excel printouts, and then in the significance section of your coefficients printouts from SPSS. So do your coefficients have an impact on sales? What hypotheses are we testing? Well, we're testing HO beta advertising equals 0 and HO beta bonus equals 0. In both cases, my p-values are less than 0.05. So SPSS shows the p-value of beta advertising as 0.000. Excel shows you it's 8.18 e to the negative 9. So that's 8 zeros and then an 8 1. So obviously that's 0. So we reject HO there. And you'd be 95% confident that advertising does have a statistically significant impact on sales, and the same can be said for bonus, looking at that p-value of 0.0165 or 0.017, depending on whether I'm looking at Excel or SPSS. Then I can do individual tests. So I'll use my t function. Again, I'm going to use my t distribution since I do not know the standard deviation of the population. So my t statistic is equal to beta that I get from my regression minus the hypothesized value divided by that standard error of the beta. And I'll have to work that out individually in Excel. Now, if that hypothesized value is 0, that will give me the p-value 2-tail, and that will be confirmed in my Excel general area printout because it tests that default. So make sure that you always run through and do that one, because then you can be sure that you have your hypothesis testing table set up correctly. For SPSS, you can test by just dividing the significance by 2 if t is the same sign as the test you want to do. So if you want to test for a positive impact and t is positive, then take significance and divide by 2. Remember, the significance is your p-value. If you want to test for a negative impact and t is negative, then take that significance and divide by 2. But if you have a positive t and want to test for a negative impact, then you would take 1 minus that significance value and divide that by 2, and vice versa. So as long as there's a match between what you want to test and the sign of your t statistic, just take that 2-tailed significance or p-value and divide by 2. If there's a mismatch, it's 1 minus that significance divided by 2. And here's the example for our bonus. So we think that bonus has a positive impact on sales. So HA, beta bonus, is greater than 0. So that's what we believe to be true. So we test HO, beta is less than or equal to 0. In other words, that the opposite of what we test the opposite of what we think is true. And then our goal is to reject that. So I set up my hypothesis testing, and I come up with p-value lower tail as 0.008. So that's less than 0.05. So I would reject HO. So my conclusion here would be to reject HO, and my interpretation would be that bonus does have a positive impact on sales. And I would do the same thing looking at SPSS. I didn't copy that in there, but you saw significance. That p-value it gave you was 0.017. Since we're testing a positive impact, we take that 0.017 and divide by 2, and we come up with that same p-value lower tail of 0.008. So again, we would reject HO and conclude with 95% confidence that bonus does have a positive impact on sales. R squared and adjusted R squared. So I've given you the equations here for what R squared and adjusted R squared do. R squared is a goodness of fit. It tells you the percentage variation in your regression, the percentage variation in your dependent variable explained by the regression. But every time you add another independent variable, even if that independent variable is not statistically significant, even if you have no reason to believe that it would have any impact on your dependent variable, R squared is still going to go up automatically just because you've added it. So the adjusted R squared takes away that artificial inflation. Adjusted R squared can, in fact, be negative if your regression really sucks. That's kind of something funny that you will very, very rarely see. But again, N is the number of observations. K is the number of independent variables. So we see that in there, just recognizing the fact that, we're accounting for those additional independent variables. And then the F test tests whether or not all of the independent variables together have no impact on the dependent variable. Basically, this is a way of testing the idea that, you made up relationships that really don't exist. And we're confirming, so if you reject HO, then you would conclude that at least one of your independent variables does have a statistically significant impact on your dependent variable. So with simple regression, your t-test for beta 1 equals 0, and your f-test were the same because there was only one independent variable. Here, they're going to be different because now we have more independent variables. So if you reject HO, you would conclude that at least one of your independent variables has a statistically significant impact on your dependent variable. And I've given you the equations here, even though this comes out default in both Excel and SPSS, because we will need to go back and understand the logic of how this works in order to do our partial f-test, which we'll discuss in a little bit. Okay, so we can see the R squared and p-value of our F statistics here. So adjusted R squared, even after accounting for the impact of the artificial inflation associated with an additional independent variable, still we see that about 84% of the variation in sales is explained by our regression. So that's pretty good. And my p-value of my F statistic is definitely 0. So that's telling me that I'm 95% confident that at least one of my independent variables has a statistically significant impact on sales. And I can conclude the same thing looking here that adjusted R squared of 84.2% and the significance of my F statistic as 0. Now, we want to compare regression models. So sometimes you have a question, you know, I think this variable might have an impact. Should I include it or not? So what you can actually do is run the model once without it, once with it, and then do this F comparison test. So you actually have to run two separate regressions, one that we'll call the full model, which has all of your new variables, and one that we'll call the reduced model, which does not have the new variables in it. Okay, so we will then calculate this F statistic where F is the number, where F is the, gives you your comparison to see, did these additional variables actually add value to your model? So K is going to be the number of independent variables in your full model, and L is going to be the number of independent variables in your reduced model. And then you'll have to run both, and then you will calculate this in Excel using the sum of standard errors from the reduced model and the sum of standard errors from your full model. Now, remember, when you're doing this in SPSS, let's go back a second. If you look here to find the sum of standard errors in SPSS, it's sum of squares, and then look at that one that says residual. Remember, residual means error, so that's where you're getting that information when you're looking at SPSS to find this. So what does the F comparison test do? HO, all of the additional coefficients are equal to 0, meaning the new the new observations don't really add any value. We don't need these additional variables. Or HA, at least one of the new coefficients, does have a statistically significant impact. And in order to do this, we'll actually have to calculate the p-value of the F statistic. So you will reject if F is less than a critical value. You will not reject if you will reject if F is greater than a critical value, and do not reject if F is less than or equal to a critical value. And you'll actually use the F inverse function to find what that value would be. So alpha is your 0.05 for your 95% confidence. K, remember, look back here, K is the number of independent variables in your full model, and L is the number of independent variables in your reduced model. N is your number of observations in total. So I'm showing you on the ANOVA table where to get SSE for your full model and your reduced model, and then use the full and reduced model data to explain and calculate the F comparison. Do these values really help you? What hypothesis did you test to arrive at this conclusion? Okay, let me go. I don't know why it's not going back. Hold on. Okay, so we will go through that example in class so that we can practice that better. There's also the video that shows going through this individual comparison. And what we will see is that it really doesn't add all that much to our regression. So we would conclude that our additional independent variables aren't going to be beneficial for us. And I'll show you that example in a separate video. Now, one of the things that happens when we add more independent variables, we could introduce something called multicollinearity, and that's a bad thing. So the X variable being highly correlated with Y, that's good, because your independent variables should be able to be used to predict your dependent variable. But your X variables being highly correlated with one another, that's bad, because then we can't interpret the impact of each independent variable individually. So what we would see is kind of an overlap. You know, is it the amount of sun that's shining that determines how hot it is, or is it the temperature outside? Well, you know, there's more sun shining, it's probably going to be warmer. I'm talking about summer. I don't know, it's the first thing that popped into my head. But when you have two independent variables that are highly correlated with one another, it's hard to be able to disentangle their impacts to see, you know, which of the two is really driving what you're observing. So how could we detect multicollinearity? If you see a large F but you have really small t ratios, so you know that at least one of your independent variables has a statistically significant impact on your dependent variable, but all of your p-values on your t statistics are coming up as insignificant, you're going, what's going on here? It's got to be that there's a multicollinearity impact in there. You can examine pairwise correlations, so looking at two independent variables and how they relate to one another. Obviously, a high correlation would indicate multicollinearity. The drawback to that is that you have to do them two at a time. Well, if you only have 2, 3, or 4 independent variables, not such a big deal. But when you're building a giant model, that gets really tedious. So the third option is something called the variance inflation factor. The variance inflation factor is calculated by regressing one independent variable on the other independent variables. So you, in essence, have to run a series of new regressions. The R squared of this regression of this independent variable on all of the other independent variables will be called R squared sub j. So it's going to be something, it's going to show the relationship. And then you calculate the variance inflation factor as 1 over the quantity 1 minus R squared sub j. So you have a problem if any individual VIF is greater than 10. Now, some people will say if it's greater than 3, if it's greater than 5. 3 and 5 are like trigger points that you're starting to see a problem. 10 is huge. Or if the average VIF is considerably larger than 1, then you're going to have a problem. We would say that any individual variable is okay if its VIF is less than the quantity 1 minus R squared for the entire complete regression. Now, what happens if we detect multicollinearity? What can we do about it? For the most part, most people, when they're running these regressions, are just using them for predictive purposes, in which case it doesn't matter. There can be multicollinearity and it's not a big deal. It's only if you're trying to disentangle the relationships, because you really need to see, are these values related to one another. So only if you're doing research does multicollinearity actually, cause a huge problem. In that case, you can take out one of the variables, or you can find a third variable that, proxies for the impact of one of the other two, but isn't related and doesn't have similar multicollinearity issues. There's also an averaging type function that you can do. So if you're particularly interested in that, let me know. You may see some of the different methods involved in some of your papers that you wish to replicate or that you're reading.